Right, and let us try to solve this question, applying the techniques that we have learned of the integration. I can see that the technique that I can apply solving this equation, it will be the separable variables, right? It's fine, you can use that. I also can see that another technique of integration that I can use is homogeneous first order ODEs. I can also use that method to solve this equation over here, this differential equation over here. If I prefer to use one of the two, it is still fine. It doesn't matter which method or technique you use as long as you get to the final answer. But I would like to start with I would like to start with this technique, the technique of homogeneous. Okay. So now remember, when you have the homogeneous, the standard form is we need to write our differential equation on one side. For example, the standard form is dy over dx will be equals to, let's say, the function of q with variable x, y, and then say that we have the function of p with variable x and y. So now function q and function p, they're supposed to have the same degree, meaning they're supposed to be the same homogeneous linear equations, algebraic equations. So in this case, if we decide to do that, so I have dy divided by dx, which will be equals to, let's see, here we're going to have y squared. Um, let me erase that. I erased everything, but it's fine. So that means we're going to have dy divided by dx will actually be equals to x squared divided by y squared. Remember, what's the reason of me writing my differential equation in this case? It's because I want to use the standard form to see if these two algebraic equations, they will be homogeneous or not. Having a look at the exponents of these two equations, they are the same. They have degree of 2, so that means they are homogeneous. Now I can apply that technique. Remember, solving equations like this, before we can even solve this, we're going to have to let, right? But the question is, what are we letting? So we have y in this function, so that means we're going to have to let our y to be equals to vx, right? Using the very same equation, I'm going to derive it, deriving y over here in respect to x. It will be dy dx, and therefore deriving these two functions, which is v and x, I'm going to have to use the product rule, right? So I'm going to keep my v constant, and then deriving x, it will be 1. Plus, now let us derive again using the product rule, like I said. Now we're going to keep our x constant, and therefore we derive v in respect to x. It will be dv dy, right? So using these two equations, what we're going to do is we're going to just do a substitution onto our homogeneous differential equation. So now doing substitution is, here we have dy over dx. So when we see dy over dx, we're going to substitute this, meaning on this side of the equation, that means we're going to have v plus x times dv divided by dx, right? Which will be equals to, we see x squared, we're just going to write it as it is. But at the bottom, we see y. So remember, we said that y will be equals to v multiplied by x. So that means over here, we're going to have v squared multiplied by x squared, right? Now, the aim here is to, after performing this substitution, the aim is to do the separable variables as much as we did before the homogeneous, okay? So what I'm going to do is I'm going to transpose my v to the other side of the equation. So doing so, this side, I'm going to have x multiplied by dv divided by dx, and if I can see that my x will cancel my x, and then here when I transpose my v on the other side of the equation, basically I'm going to have 1 subtract v to the power of 3 divide by v squared. Okay, if you transpose this v on this side and then you add it to 1 over v to the power of 2, basically this is what we are actually going to get, right? Now trying to separate the variables with their differentials. This is what we're gonna do, separable variables. So on this side, I'm going to multiply with this reciprocal, right? Me multiplying with this reciprocal so that I can get rid of it, but this side I want it to exist so that I have dv. So that means I'm going to have v squared divide by 1 subtract v to the power of 3. Let me close them inside of the bracket, multiply by dv. And then on this side, I'm also going to multiply by the reciprocal of x so that it moves with dx. So I'm going to have 1 over, let me also close it in bracket, 1 over x dx. Now we can see that our variables are then now being separated. So now after separating these variables, which function are we going to perform? We're going to integrate this side in respect to v, and then we are also going to integrate this side in respect to x. So now integrating this side, applying all of the different integral rules or techniques, make sure that your integration techniques are on point. So how are we going to integrate this? Is there a specific way to integrate this? We can see that we can use the u substitution, right? If we want to use the u substitution, what are we going to do? We're going to we get the function at the bottom. We're going to let u to be equals to 1 subtract v to the power of 3y, so that when we differentiate this, we will be able to get rid of v squared, because we can see that here we have v to the power of 3. So when we differentiate v to the power of 3, we're going to get v to the power of 2, and it will match with that v to the power of 2 so that they can cancel off. We get rid of the other one. So now from this equation, let us perform differentiation. So du dx, it will be equals to negative 3v to the power of 2 dx, right? So now we also know that this, it can be written as negative. I want to make dx subject with the formula, right? I can write it as negative 1 over 3v squared du, which will be equals to dx. Now, after using my u substitution, this is what I'm going to do. I go back to the function that I was working with because I want to perform integration. But before we perform integration, we're going to have to substitute dx. No, actually, here it's supposed to be dv, not dx, okay? Here it's supposed to be dv. My bad. I take that back. So here it's supposed to be dv. Remember, we differentiate in respect to v, not x. Now here I'm gonna perform my substitution. I'm gonna substitute my dv. When I substitute my dv, I'm gonna have this whereby v squared will cancel v squared. Continuing with my constant is gonna be negative 1 over 3. Let me take it outside, 1 over 3. The integral of, now I'm gonna have 1 over u. Remember, because 1 minus v to the power of 3 will be u du, right? Which will be equals to the integral of 1 over x multiplied by dx. Now let us integrate this. Now integrating this side, 1 over 3, integrating this, we're going to have lim of u. You can write your, you don't have to write your constant, okay? You can write your constant only once, because say, for example, the constant at this point, I'll call it C1, and the constant at the side, I'll call it C2. Eventually, when I transpose C1 to C2, when I add them together, I can just somehow call them C. You understand what I'm saying? And therefore, differentiate, integrating this, here we're gonna have lim of x. Now we can write our constant, which is C. Remember, this C could be combination of this and that constant, okay? So it really does not matter. And therefore, remember, we are not looking for our general solution in the form of u, but in the form of x and y. Remember, we have already mentioned that you can also introduce your constant as lim x if you want to determine your general solution explicitly, where you would make y subject of the formula. But just determine general solution can just end here, where we're going to have to substitute u to v, and therefore from there to v2, okay? So that means here we're going to have 1 over 3 lim of, remember what is v, sorry, u. Our u in this case, it will be equals to 1 subtract v to the power of 3, which is equals to lim of x plus c. You can, like I said, you can just write lim c, okay? It's still fine. And therefore negative 1 over 3 lim of, remember what is our v? From this equation, remember this can also be written as y over x will be equals to v. So when we see v, we're going to substitute that. That means we have y to the power of 3 over x to the power of 3 ln is equals to ln of x plus c. And therefore this, it will be our general solution. Now let me tell you this. Having a look at this differential equation, you can also use separable variables from the get-go. It is still fine, it's still applicable, it will work. But here, you're not gonna get the same things because, in fact, you're gonna get the same things, but it won't see, maybe if you wouldn't be able to understand, you wouldn't see different things because here, in order for us to get the same thing as this, when we use the separable variables, we're gonna have to solve this. Okay, and I have to get rid of the natural logs so that we can see that this equation it's gonna be the same as that one. Okay, and I hope that was clear.